each game or season might be considered an observational study, right? Usually we wouldn't think about it as any kind of real randomized experiment, although you could if you had a coach who was really willing to experiment with you. The scorekeeper and the player tracking cameras might be the instruments from which we're getting potentially noisy measurements. And then from that perspective, all basketball metrics that we actually collect, we should think of as measurements, and we should not think of them as perfect reflections of reality in some way. So we just started with that basic notion and really asked how reliable are different basketball metrics and what can we learn from them. So I just thought I'd start with a little bit of background on this paper we published a few years ago called Meta-Analytics, which was really aimed at trying to address that question. A little formatting issue here. So the basic idea was we said, okay, let's actually look at the metrics that people are using to learn about the game of basketball and see if we can, rather than quantify basketball, quantify the aspects of these metrics themselves. And we came up with three metrics, and I'll talk a little bit about those in a minute. And the goal at the time was not to actually introduce any new way to do analysis, just to think about what we could learn about the metrics that are currently in use. What I'm going to talk about in the second half of the talk is really how then we might think about designing better tools for analysis based on these metrics. Okay, so the three we came up with were discrimination, stability, and independence. Discrimination was basically just asking the question, how much does a particular point estimate actually reflect differences in skill across players as opposed to just chance variation? So that's a pretty natural one if you're a statistician, because we're used to quantifying uncertainty, but it's not something you see talked about in any real sense when you watch sports on TV or read like sports journalism, unless maybe it's something like 538, which is really sort of statistics and sports focused. The other one that we talked about was, okay, well, if I'm looking at a particular metric like, let's say, wins above replacement, how much does that vary over time? And is it predictable in the way that it varies over time? So we could characterize the stability or the predictability of a particular metric. Because if someone is really good, this year, but it's not predictive at all of how they're going to be next year, then that's something we should know when we're thinking about, for example, drafting a player. And then the last one is that so much of sports analytics is about like deriving new metrics that tell us, hopefully tell us something new. The question though is, does it? And when we consider a set of metrics together, how much kind of unique information is actually in that set? Or another way of framing that is, how correlated are different metrics for skill? So I have a diagram it's a simple diagram. I actually like it a lot, just conceptually, for the way I think about the challenge of modeling player ability in basketball. So the way I think about analyzing basically box score data is that you've got a tensor. Okay, so like a 3D array. You have players. You have different metrics: field goal percentage, rebounding, maybe some advanced metrics like box score plus minus, or some version of WAR, wins above replacement, and then you have time. Okay. Now, going back to that perspective of these metrics reflecting measurements, well, let's actually think about what these measurements actually reflect. Well, the way I like to think about it is that we have some latent skill associated with a player, and we could conceptualize that skill as maybe agility, athleticism, some technical skill like shooting ability. Those skills are, of course, observed in the context of the team. So there are potential team effects, and then things like sampling variability or chance. All of these are inputs into our measurement process. So when we look at a particular cell in this tensor, we're seeing some mixture of these latent skills confounded by potentially things like team effects, and then of course, subject to sampling variability. Okay. So I think that's something we always want to be aware of when we're analyzing this kind of data. Okay, so just going back, I thought I'd briefly review the meta-analytics that we presented in this paper a few years ago. So the first one was discrimination, and this was partially motivated by just a nice, relatively simple presentation by Rob Arthur in 538, looking at the MVP comparison between Trout and Donaldson in 2015, looking at wins above replacement. This is a baseball metric. And what's really important, right, rather than just considering the point estimate, is to have some notion of the uncertainty about that estimate. And so what they did was they essentially just bootstrap resampled every game in the season to create a density representing the uncertainty of those players' true WAR value in some sense. Okay, so we decided to take this idea and generalize it to some notion which we call discrimination. You can think of this as an R-squared style metric. It's basically 1 minus the chance variability, sampling variability, over the total variability across players. So let's say I'm looking at 3-point percentage, one that I'll talk about a little bit. The total variability is just take the point estimate of 3-point percentage across all players and compute the variance of that quantity. The chance variation would be like, if you're assuming a binomial model, then it's just the variance of p hat, the maximum likelihood estimate of the binomial. You could also get at that through bootstrapping. So if most of the variation in 3-point shooting that we see comes from chance, then the discrimination is very low. So that's something we might be interested in. We actually did this a few years ago, looking at 3-point percentage, which is we found to be one of the least discriminative metrics. So it's kind of interesting to think about because there's a lot of storytelling around 3-point percentage. But what you see here are densities showing our uncertainty about the true 3-point shooting percentage, assuming that within a season, for example, 3-point shots are approximately IID. You see that across all these players, there's significant overlap. And so a huge amount of the variability we see in differences in 3-point percentage are actually due to sampling variability rather than differences in shooting skill. At least that's what we found. As I mentioned, another question we might think about is how stable or predictable a metric is over time. So this is kind of thinking about, okay, assuming we can remove chance variability, let's look at the variance of a metric between seasons divided by the total variance of that metric across seasons and players. So just showing an example of a player that seems to have very stable field goal percentage over these 4 years, but maybe does not have seemingly stable or predictable true shooting percentage. Now, this is just raw empirical true shooting percentage. So it's not immediately obvious whether this is due to chance variation or something else like change in context or actual change in skill or change in approach to the game. But that's something we want to understand. So we have, if you go to the paper, we have formulas for approximating these quantities, or at least we define these estimands, discrimination and stability. One of the things I just want to show you is that, as I emphasized, 3-point percentage was one of the least discriminative metrics we found. It's a very high variance estimate. But you could also interpret things like, okay, free throw percentage is not particularly discriminative, but it is quite stable. So what that says is that, okay, the free throw percentage, true free throw percentage or skill doesn't vary that much across players in the league. In fact, most of that variation you see is sampling variability, but within a player, it's that true skill is relatively stable over time. So a player's free throw percentage is not evolving that much typically. Okay, and then you see other metrics that maybe are very discriminative and stable, and it would be worth knowing that. Okay, so one of the things that we might want to know then is how can we come up with improved metrics based on some of these criteria. This is a slide that makes it into almost every sports talk I give. Now it's almost like a joke I have with myself to just make sure it makes it in. This is a paper, comes from a paper in 1975 by Carl Morris and Brad Efron. So Carl was I was lucky enough to take some classes with Carl on this very topic, on hierarchical modeling and shrinkage estimation before he retired. But I just think this is like one of the coolest examples of sports in statistics ever. But also, I mean, the fact that such a profound and important idea was illustrated using sports, I think is kind of telling. So essentially what's being shown here is empirical batting averages in the MLB. And you can see after, like, let's say the first month of the season, there's quite a bit of variability between players. And then again, it's the same question. How much of this variability is due to sampling variability versus actual variance due to the ability of these players, the hitting ability of these players? Okay. And the idea of the James Stein estimator is that there's an approach to estimating these quantities based on shrinking these estimates towards some global average. And that is provably going to be a better estimator for the overall mean squared error of your, let's say, batting average across all players. You're not guaranteed to get a better estimate for any individual player, but quite likely to do much better. When estimating the MSE for a group of players. And the intuition should just be, if you think about the estimates, the raw estimates that you see, the variability here is due to signal variability plus chance variability. And if we have some clever way of kind of accounting for removing that chance variability, then what we get hopefully is a series of estimates whose variance is closer to the signal variance that we're targeting. Okay. So this is going to be a big part of how I think about improving these basketball metrics. All right. So one of the things I did was I used, this is actually output from software developed by one of Carl's students that basically does a slightly fancier version of James Stein shrinkage estimation. So here there's a binomial model for three-point shooting. I'm looking just at LeBron James, and I apply the methodology, and it shrinks three-point shooting down to closer toward LeBron's global average. So this would be kind of under the assumption that most of the variance we see in three-point shooting over a player's career actually is largely chance variation, and so we can get a better estimate of that true skill by shrinking them toward the global average here. So if you do that, this is the empirical Bayes estimate of three-point shooting for all players on my stability discrimination plot, which shows that now I've actually got a metric which is more discriminative and more stable. It's still not great, but I've potentially come up with a metric that's better than just raw field goal percentage. It's not too surprising that we might be able to improve upon that. Okay. All right, the other big piece of what I'm going to talk about today is this idea that there's a lot of redundancy in the metrics that we have for basketball. In this particular analysis, we looked at 65 basketball metrics, and we came up with relatively simple way to estimate the correlation between these metrics, accounting for the fact that there's some difficulties due to, for example, some of these metrics looking very, very non-normal. I'll see if I can kind of highlight a few things. So part of, I'm going to see if I can zoom in here. So these box score plus minus in value over replacement, maybe I'll even draw this bigger cluster. There's a cluster of metrics that are all meant to measure overall skill in some way. They don't appear to be all that different. The reason this might be important is that we might want to know if you're looking at a metric and you're saying like, hey, this player is excellent at offensive rebounding and excellent at blocks and excellent at dunking. They must be really amazing. Well, we watch basketball and we know that those things are all highly correlated with height. And so a huge part of what those metrics are capturing is the position of the player or, or height, right? When we think about those latent attributes of players. So can we do something to account for the relationship between these metrics? And I can actually show you, right? There's these clusters of rebounding next to blocks over here. So we can see that these things are correlated. The other aspect of this I might mention is that these are like the overall skill metrics here are pretty close in this dendrogram, this cluster dendrogram, to things like field goal percentage, which is something else some of my past work using player tracking data was focused on this imbalance between offensive metrics. There's more of them, it's easier to measure, compared to the relative importance of defensive metrics, which is just measuring defense is just very hard. Measuring individual contribution to defense is very hard. Okay. So I know Mark mentioned that we'll hold questions to the end, but feel free if you have questions at this point to drop them in the chat or jump in. That'd be great. Oh my gosh, I see Kevin Rader. That is a face I have not seen in 10 years. Okay. Okay, so coming back to this picture, the idea is, okay, I presented a few metametrics, ways for characterizing the quality of metrics. An ideal metric would be one that actually introduces some new information. I learned something new from it. But it's also potentially discriminative about player ability and either stable or predictable over time. Okay. The stability is important if, in particular, if you're looking at selecting a player for your team, either drafting a player or trading, you want historical performance to be predictive of future performance. Okay. So from this perspective, what we have to do is try to come up with some method to jointly model all of these metrics over time and across players. So you could view this as modeling a tensor. There are a bunch of challenges that are not so trivial. A few is like part of this diagram. I've thrown some NAs in here. So players get injured, right? You might lose a player for an entire season. If you're modeling the data at the game level, I'm showing season level, but at the game level, you'll of course have players who are out for periods of time due to short-term injuries. And as noted, like the effect of chance is you have to deal with heteroscedasticity, right? Because players play for different amounts of time. And so if I look at three-point shooting percentage, I'm going to get a much better picture of Steph Curry's true skill than I am for someone who might take just 50 threes in a season. Okay, so that motivated the new work that I'll show you the sort of beginnings of today. It's been significantly more challenging than I anticipated. So unfortunately, I don't have the polished results to share with you today, but I think there's some maybe interesting ideas that are at least worth sharing. So the aspect I hadn't really dealt with in the past was thinking too much about the time series component. And so there is a bunch of literature on production curves. Basically, how do I model a player's production over time? You may have seen it called an aging curve. I choose not to use the word aging because I don't want to presume that change in production is driven by age. It could be other things. It could be that you're practicing and picking up new skills. But basically, the idea is to predict future trajectory of a player's ability and or to characterize similarities in these trajectories across time. So let's say I'm looking at like a metric that measures overall skill, call that Y. Then I want to quantify for each player at time t how that metric is evolving. So I have some function which says for that given player at some time that tells me how their mean performance changes over time. And that's roughly how you can conceptualize the production curve methodology. There are a lot of different methods for doing this. If you read 538, they have an algorithm called Raptor, robust algorithm for using player checking, on-off ratings. I couldn't find a ton about what they actually do, but as far as I can tell, they use a nearest neighbor algorithm to characterize similarity between players. So they just kind of look at these time series, they do nearest neighbor matching between the players, and then what they more or less do is to predict the trajectory of a new player. They represent the predicted trajectory as a weighted combination of trajectories of players that have sort of progressed further in their career, is my sense. There are other methods that do this in a slightly more rigorous way, or at least the research is published. Something called the method of archetypoids, which is actually to take just a few canonical players' trajectories. Like imagine they're like points on a convex hull, and then you represent another player's production as some linear combination of those, like let's say 4 canonical players. And so you could kind of map everyone's trajectory as a point inside this convex hull of these canonical trajectories. There are also some really great papers on Bayesian hierarchical modeling for production. There's a really, I guess, sort of important paper by Barry et al. From 1999, which is an attempt to address this kind of age-old question of like who's the best overall time. So they basically say in their paper, literally, their goal is to build this statistical time machine. So you can say, you know, is LeBron James better than Michael Jordan? So they're doing this production curve modeling, but also accounting for the fact that, you know, the way players play is evolving over time across, you know, across seasons. And they're trying to use overlapping players to try to somehow make some statement about players that played in different eras, which one might be better. It's a pretty ambitious project, I'd say. And then the other one is by Garrett Page, who uses hierarchical Gaussian process models for evaluating position. So I'm going to talk about a Gaussian process approach that I have in mind, which is closely related. Their idea there is that you have some mean Gaussian process by position, and then some residual, and you kind of basically the estimate was to infer the production curve for overall skill for different positions, and show how production changes by basketball position. Okay, so the majority, basically all, I would say, of the existing literature I could find in this area is focused on some measure of aggregate skill, some measure of overall skill. So part of my idea when I was thinking about modeling this tensor is, hey, I want to measure, okay, this time series, but also across all metrics, because I want to account for the fact that these metrics are correlated in some way. If you imagine like Garrett Page focused on game score, which is a linear combination of box score metrics meant to measure aggregate skill. So you could look at developing production curve methodology for that metric, but then the question might be, well, how do other linear combinations evolve over time by player, and what might that tell us? Does that tell us something different that's also potentially interesting? Okay. So now we're going to think about a multivariate Gaussian process. So we'll think about modeling a metric I for player P at time t using some, let's say, Gaussian process or time series methodology. So that's the idea I had in mind for this analysis. Okay. All right, so just summarizing the what I've covered so far. Innate player ability can evolve in time, and that's what we want to capture somehow. And part of my idea is that, well, things like athleticism might evolve very differently than traits like skill traits, right? Like you always hear that Michael Jordan says, like, mentally he's still as sharp, he's still got the shot, it's just his body's wearing down, right? So you can imagine that those are different latent trajectories. They've evolved differently in time, and those are going to translate to, in some way, a time series for one of these measured values of skill. Okay. The other thing is that context changes over time, your team changes, the way the game is played changes. We have to account for sampling variability. And also this idea that these different metrics can and do measure aspects of the same latent or innate ability. Okay. So when I was thinking about like what I want for a method when I'm thinking about modeling this tensor, which I've now come to the conclusion was potentially ambitious, or maybe I just need to kind of rethink my approach a little bit, I want to do joint inference for potentially non-Gaussian outcomes. So I've got all these metrics. Some of them are plausibly Gaussian, and some of them are clearly non-Gaussian, right? Like might be better approximated by a Poisson if they're based on rates, or binomials if they're really characterizing successes given some number of attempts. Okay, so I want to model mixed data, essentially. It's the term for modeling data of different sort of distributional form. And I want to do it jointly by accounting for dependence between metrics, by accounting for similarity between players, so recognizing that some players are more similar to others, and account for the temporal autocorrelation. So you can imagine, like, based on my sort of setup for the meta-analytics, I had dependence as one meta-analytic, right? I had kind of characterizing how well we could discriminate players based on a metric. So this is discrimination. And then stability, which I think maybe a better term now would be like something more like, I don't know, predictability, but basically how well can I actually capture the time series, future time series for a metric from available data versus like how much irreducible error is there. Okay, so these are the ideas, and then also for dealing with chance variability, the fact that this is really heteroscedastic. So I need to incorporate for each player metric some notion of sample size or exposure, like how many minutes have you played in a given season. Okay. So I think there's a lot of pieces here. Okay. All right, so following some previous approaches, the work I've been doing is based on Gaussian process regression. If you're not familiar with GPs, the basic idea is that you're going to model the data as a random function. And that random function is jointly multivariate normal with some covariance k, covariance kernel k, where the entries of k represent the covariance at different time points, t and t prime. And usually you'll parameterize it with, for example, a covariance function like the squared exponential. So this says, the further apart in time the two observations are, the less correlated they are. And you can play with these covariance functions to get, smooth functions or functions that are highly correlated, but kind of non-differentiable, or there's a whole range of things you can do with the covariance function. But I'll be focusing on the squared exponential, which gives you infinitely differentiable smooth curves. Okay. Okay, so there's a few ways of thinking about now modeling all of these metrics over time. And in the machine learning literature, this is called a multitask Gaussian process. So in short, for each metric I, I'm going to model the time series as some linear combination of latent Gaussian processes, latent functions. So the metric is just some linear combination of latent functions. And these W's, these weights, are going to reflect the correlation. Sorry, this should say metrics, the correlation between metrics. Okay, so I can actually account for the fact that some metrics might be more correlated than others, and I'm going to have to learn those weights. This is called the linear model of co-regionalization if you're somebody who's involved in like spatial statistics or like geostatistics. Okay. All right, so that's just like focusing on a metric, ignoring player identity. I could flip it and say I'm going to focus on one metric and do the same thing for players. So same idea, a given player's trajectory, just like we saw before with the archetypoids, in slightly different formulation. I'm going to represent a player's production curve as a weighted combination of these latent curves. That's basically what that says. And then these W's tell me the correlation between players. So if two players have very similar W, then that means they're like, just think of it as a factor analysis. They're loading on the same latent function, so they're highly correlated. They're going to have similar trajectories. Okay. All right. Now what we want to do is combine them in some way. We want to model both tasks and players. So effectively, this amounts to choosing a covariance function, which gives me the correlation between any player for any metric at any time with any other player, any other metric at any other time. And the way we're going to do this is using this kind of separability argument. So I have a separate covariance function that just accounts for smoothness in time, and then some other weight that might tell me something about the similarity between players and metrics. And I think this is where a lot of the real difficulty is going to come in, is how exactly to parameterize this covariance function, the right way to do that. Because you clearly have quite a few parameters. I mean, you could easily over parameterize, because this is like a number of seasons by number of metrics by number of players squared covariance matrix. And that's why you do these separability, make these separability assumptions to try to reduce the parameterization sum. Okay. Or in other words, make this covariance function low rank for computational convenience. Okay. So that's how I'm thinking about modeling this tensor data. Now, as I mentioned, depending on the metric, we might want to use a different link function if I'm thinking about this in the GLM framework. So I have Poisson outcomes, like anything that's like a field goal attempts or steals or blocks. I'm just saying those are approximately Poisson with rate that's a function of your exposure being minutes. So here's the minutes for a given player. And then we have this function that's learned from this multitask GP. It's player metric specific. Okay. And when you're doing like the Poisson GLM, right, you're modeling the log rate. So that's sort of like a natural formulation. Same deal, like if I want to model field goal percentage, or rather I should say number of made field goals, I could condition on the field goal attempts and then do a logistic regression for, or rather model the make percentage as on the log odd scale. Okay. So I got like this multitask GP, which connects these latent Gaussian processes and then these link functions depending on depending on the metric, essentially. Okay, and then of course Gaussian outcomes. There's some things that that are well approximated by Gaussian. I used plus minus. I'm modeling as Gaussian, and the variance at any given time, I'm scaling by inverse minutes, right? So the way to think about that is if I have observed a player for an infinitely long time within a season, I would know their true skill. So this accounts for the fact that certain players I don't observe that much, if they haven't got that much playing time, then I'm going to have a lot more uncertainty about the true skill. Any questions about that formulation? Maybe I'll pause there. Okay. Okay. My idea was to do this using the fully Bayesian approach. In particular, I guess maybe I should back up a little bit. So Gaussian processes are notoriously difficult to fit to large data sets because they involve inverting potentially large matrices, and inverting is computationally expensive. It's order n cubed. So there's, if you do GP research, which I don't really, a huge part of the work is coming up with approximations or tricks to kind of circumvent that inversion, so you can fit these GPs to large data sets. Okay, I found a paper with my colleague David Arbour, who's helping me with this work, which is has an implementation in STAN. If you've done Bayesian modeling using probabilistic programming languages, and they use a basis function approximation to Gaussian processes. And the advantage is that you can model these GPs in this latent space, and then it's going to work well with non-Gaussian observational models like Poisson and binomial, as I alluded to. Okay. I know I'm getting near the end, so I don't want to go into the details too much. You can read this paper. It's a nice paper if you'd like. I'll put it up at the end as well. But the basic idea is to kind of convert it into a problem that looks like linear regression, right? So if you think about these as your, let's see, I want to make sure I have this right. If you think about this as your x, then you have to learn these betas. Then it's essentially just a regression problem. So you have these basis functions x, you are learning the coefficients beta, and this is going to be approximately a Gaussian process. The trick is that the x's are not fixed. They're actually also random. And that's because the basis functions you use depend on how smooth these curves are, and you want to try to learn how smooth the curves are. So that's like the 5-second overview of this, this paper. Okay. All right, so this is where I did not make nearly as much headway as I had hoped. So I'll show you some like very preliminary analysis. I was working hard this week to get some new results, and they didn't pan out. So I don't want to show you something that's not totally legitimate. But one of the things that we tried to do, I'll try to show you this here, is I mean, you can think of this as basically principal component analysis. Or what we call functional principal component analysis, because we want to find scores for players or weights that mix with these latent functions or the principal components, the eigenvectors, that describe variability across players. And then also we can imagine scores by metric. So this is some of the preliminary results that we have characterizing differences in all of these metrics across time. I'm reasonably happy with the way this is kind of with the direction this is heading. So you've got, let me see here. You've got some of the like centers and big men out here, some 3-point shooters, Dirk Nowitzki and Kyle Korver at the top. And if you actually look at how these things load on different metrics, I can show you this in the next slide. The first principal component, which was the XY direction, that was the one where I circled the centers, loads heavily on these skills, these trajectories associated with like blocks and rebounding, and negatively with 3-point percentage. And then the second principal component, which I showed like Kyle Korver and Dirk Nowitzki, these were people who were taking a lot of threes and maybe adding some value. So it's sort of like a different orthogonal direction. I should note that part of the reason this is challenging is because this is not just like PCA or functional PCA, it's Bayesian functional PCA. And doing Bayesian PCA, I've worked on Bayesian PCA in different ways, in different kinds of projects. It's surprisingly difficult. So you have to learn a posterior over the scores and the eigenvectors. And there's a question about whether you want to try to encode the like orthogonality constraints in your sampler. So there's lots of nuances there. Okay, so I'll show you, just briefly show you these average production curves that came out of this analysis. So this is like on aggregate. And the width here, basically these are posterior samples of these functions. So they're somehow representing uncertainty. I'll draw attention to a few of them, like here's plus minus. So you can see that like plus minus is peaking at around age 28 or 30. There are other interesting trends that I wouldn't want to necessarily bet my life on at this point. I think there's more work I need to do to verify this. There's a lot of pieces to this. You know, I think it is worth looking at some of these things. So I guess things I want to highlight are basically that, okay, there are correlations between some of these metrics over time, like plus minus and field goal attempts might be loading on largely the same latent attributes, right? Like you tend to shoot more if you're a good player, and your role evolves with time as well. There's other things like, okay, without maybe reading into this too much, right? Like blocks start to decrease with time. So this is where I might hypothesize similarly rebounds start to decrease with time or with age, that maybe these are skills that require more athleticism. So they're more susceptible to the effects of aging than something that's like maybe more stable, like free throw percentage. Okay. So that's kind of where I am with this. You know, again, I want to say that I'm still doing a lot of work to verify all this, but you know, we have some initial predictions, and we can overlay the empirical empirical metrics for like an individual player and see how well these curves fit. In the like last 5 minutes, if you'll give me that, I want to just mention two things and just broaden it out again. So as far as this particular analysis goes, I'm hopeful this will turn into a nice analysis in the end. I'll have more kind of really interesting results. Part of what I really wanted to show today that I didn't get ready was you can imagine once you have this latent space, now you have like a slider and you kind of slide up and down in this latent space, and you see how, like imagine you build a widget and you say like, I'm going to slide more towards Kyle Korver, or I'm going to slide more towards Shaquille O'Neal. And you have this kind of grid of production curves, and you see how they like, you know, like shift either kind of when the peak is, or they flatten depending on the predicted production curves across all metrics based on that like PCA plot. Okay, so there's a bunch of challenges, MCMC, computational efficiency, selecting the model complexity is something I don't have a great sense yet of how to do. So that's like the rank of these kernel matrices. And then there's all sorts of non-identifiabilities that you get with the usual kind of factor model problems, like kind of, you can always rotate the latent functions and rotate the scores, but that gives you the same predictions. Okay. Let me just see here. Okay, so there's a few a few things that we can do with this. We could start to answer those questions about the meta-analytics, like this approach, because we're kind of modeling everything jointly, could tell us about the discriminatory and sort of predictive power of different metrics. It allows us to quantify uncertainty in a way that we could really maybe say more about player ability. And then maybe an interesting direction that I haven't thought about really at all yet is counterfactuals. Like, could I use this to, like I only plug in Derek, or let's say Klay Thompson, so he just had this injury. I plug in his career pre-injury, and that allows me to extrapolate, how his performance might have gone if he didn't get injured, right? Like, and say something about the effect the injury had on their career. Okay. To wrap up, I wanted to note I have the basketball paper that I published this year is not related to anything I've talked about. It's a review paper. It's now in the annual review of statistics and its applications. This was a really fun paper to write because we got to dig into all of the literature we could find on basketball analytics, and then had the leeway to kind of give our own kind of perspective or flavor on the field and where it's going. So what I'll say in this last little bit is that after doing that paper, writing that paper, and I encourage you to take a look at it, I was sort of left with the opinion that one of the major growth areas for sports analytics in general, but basketball analytics to the extent that that's my focus, is causal inference. So we already have these notions of things like wins above replacement, like how many more games would the team have won if I replaced LeBron James with an average player? That's explicitly a causal question, but it doesn't really get the causal treatment it deserves. There's also things like the role of confounding factors related to space, time, context, like team, who the role players are, that I think are very challenging, but again, could be well understood with some causal thinking. Strategic and game theoretic considerations. So I think I saw that my friend Nate Sandholz is on. He has a nice paper that's starting to deal with some of these things. So if you're a student in the sports analytics club, this is an area that I would say there's a lot of room to make impact. It might be a place to start. Okay, so I'll just leave it there. I know it went a little long, so thank you. Here are some of the references from the presentation, and I'd be happy to take any questions.
Let's thank Alex. Thanks a lot, Alex. That's great. Did anybody have any questions? Please raise your virtual hand. Brian, you want to go?
There we go. Hold on.
That was a clap. Sorry. Not a question.
Okay, so Brian Cocoliccio.
Almost. You guys can hear me?
Yep.
Beautiful. I put it in the chat, but I'm curious how the metrics would look versus minutes played, instead of or in addition to age, because different players are playing more minutes. For instance, I mean, you had LeBron James there. For his age, he's probably played many more minutes than possibly some other player at his particular age. So that's going to have, I would think, an effect on performance. And I wonder how they would look, either, it's almost like a 3D plot, or instead of, age.
Yeah, it's a great question. So actually, if you look at this Garrett's paper, he actually looks at per game minutes played, not at age. So he explicitly normalizes or rescales everyone's career according to the cumulative minutes. So it's a different perspective, I think. You're looking. It's equally valid. I think it really is focused more on the effect of sort of the cumulative stress of just playing more minutes. You could argue if you wanted to think about production as something that might change with time, with actual, real time, then the more time you have, the more time in the gym, the more time in the off season that you're able to practice certain skills. That would be a slightly different thing. But I think it's a good question. I mean, it's something that has been looked at a little bit, and it's not something I did for this analysis, but certainly could do. I mean, the other thing that's sort of interesting is that maybe it's a different direction, but minutes is also highly correlated with all of these metrics, right? Like the better players get more minutes. And so that's a sort of non-trivial complication as well when you think about the effect of scaling by total minutes.
Laurie, you want to ask your question?
Yeah, thanks. Maybe you mentioned this and I just missed it, but how did you choose the number of latent attributes? I think it was the parameter R.
Yeah, well, I didn't mention it. I don't have a good answer for it, is why I didn't get into it. So right now I'm at the point where I'm still just experimenting and sort of making sure I can recover some sensible predictions. I think that's the $1 million question anytime you're doing any factor model or sort of PCA based on supervised learning, right? Is how do you choose the rank, or how do you choose the number of latent functions? And it's an extremely difficult question, I think, in general. So yeah, unfortunately, that's the question I don't have an answer for at that point. Other than that, I picked the rank. So I think, I mean, one of the things, if you go back to the average, the curves are very smooth. So here I took I think I had 4 latent functions. There weren't very many. I mean, it's not like these are extremely complicated trends, right? There's there's some things that sort of peak, look roughly quadratic. There's some that are monotone increasing or decreasing. Maybe you have a location shift, but it's a good question, and it needs more. Need to think about it more is the answer. Yeah.
Thanks.
Yep.
Yeah, Alex, let me ask the final question since we're going to
Sure.
have to disengage in a moment. So one thing that's related to the work that you're doing that I've worked on a little bit with some of my students is that you have these situations where players, some players have longer careers than others, and then that's going to influence some of the measurements that you're using in your modeling. And so, for example, in the figures that you showed, I noticed that there was a little bit of an uptick at higher ages, and that's probably a survivor effect. I'm just wondering if you had any thoughts about how to address that, particularly blocks. I noticed that was pretty noticeable.
Yeah, there's these kind of funny things at the edge here, these edge effects. Defensive rebounds looks like something funny is happening here. No, that's a great question. I think it sounds like you've thought about this probably a little bit more than I have at this point. But these edge effects, these survivor effects are important. The players who make it to 40 years are probably very different than the average player. So no, that's not something I've explicitly accounted for. And again, I think it speaks to maybe my ambition when starting this project, right? I was thinking hey, I just this multitask GP, let's do it. But the more I dug into it, it's you're right. There's the survivor effects, there's the heteroscedasticity, there's mixed data, there's player correlation, there's metric correlation. I kept adding on things, and I'm thinking wow, I'm trying to tackle maybe too much at once. So I like this project a lot conceptually. I'm really hoping I can get a product over the a working application that over the finish line, but there's just a lot of pieces to it. So it's a great question.
All right, let's give Alex a final round of applause. Thank you so much, Alex. And so we're gonna have our final meeting in 2 weeks, and so you'll be seeing notes sent around for our last talk. So thanks, everybody.
Thank you.